In this video, I want to have a look at simple harmonic motion problems that involve velocity in terms of displacement. So the velocity of a particle moving in simple harmonic motion can be given as this. So v squared equals n squared outside of a squared minus x squared. So we're going to go through and prove that. We know that if something is moving in simple harmonic motion, then the acceleration is given by minus n squared x. So we can integrate that because we know that a half v squared is equal to the integral of minus n squared x dx. If we integrate that, we'd have minus n squared x squared all over 2 plus c. I'm going to go through and times everything by 2, so I'd have v squared equals minus n squared x squared plus, I'm just going to call this constant c1 now because I've doubled my original constant, so it's a different one, so give it a different name. And then once we've got there, we need to figure out what that constant is. If something's moving in simple harmonic motion, then we know that when velocity is equal to 0, we know that velocity will be equal to 0 when it's at its maximum displacement. So remember that we usually write simple harmonic motion as x equals a sine nt plus alpha, or we could have cos instead. And that value of a, that's what's going to give us our maximum displacement. So velocity is going to be equal to 0 when x is equal to a. So that means our equation is going to become 0 is equal to minus n squared a squared plus c1, which means that c1 is equal to n squared a squared. Now if we pop that back in here, we'd end up with v squared equals minus n squared x squared plus n squared a squared. If I pull out my n squared as a common factor, then what's going to be left inside, I'm going to rewrite it in a different order. So I'm going to have my a squared and my minus x squared. And that's what we were aiming for. So we know that it can be written in this form, and that's going to help us with certain types of problems. Right, so the one example we're going to go through says a particle is moving in a straight line with simple harmonic motion. We know two things. We know that when the displacement is 1, the velocity is root 5. And we know that when the displacement is 2, the velocity is 2. We're asked to find the length of the path that that particle traces out and the period of the motion. So we're going to use what we just figured out. We're going to use the fact that v squared equals n squared outside of a squared minus x squared. And just keep in mind that this a is going to tell us its maximum displacement from the equilibrium point. And the n is what's going to help us figure out our period, because the period is always 2 pi divided by n. Right, so we need to figure out what those two values are then. What we're going to do is we're going to do simultaneous equations. So we're going to substitute in the values that we know. So first we'll do these ones. So we'd have root 5 squared, which would just be 5, equals n squared outside of a squared minus 1 squared, which is just 1. And we also have, if we use these ones instead, we'd have v squared, so 4, is equal to n squared outside of a squared minus 2 squared, which is 4 as well. So I'm going to rearrange both of these to make n squared the subject. So I'm going to have n squared is equal to 5 over a squared minus 1, and n squared is equal to 4 over a squared minus 4. So I'm going to call this one equation 1 and this one equation 2, and then I'm going to substitute 1 into 2. Which means I'd end up with 5 over a squared minus 1 is equal to 4 over a squared minus 4. If I cross multiply there, I'm going to have 5a squared minus 20 is equal to 4a squared minus 4. If I rearrange that, I'd end up with a squared. If I minus 4a squared from both sides, add 20, and I'd have 16, which means that my a would be equal to 4. Now I can sub that back in. And I can sub it into either one, but let's just go with number 1. So I'd have n squared is equal to 5 over a squared minus 1, which would be 5 over 4 squared minus 1, which is 3. No, it's not. It's 15, which gives me 1/3, which means that my n would be equal to 1 over the square root of 3. Now these two numbers are what's going to help me figure out my length of my path and my period of my motion. So for part A, the length of the path, this is the maximum. So what that means is that from my equilibrium point, I'm going up 4, but I'd also come back and go down to -4. Okay, because it swings equally on both sides of that equilibrium point. So that means that the length of my path is 8. Now I think it was originally in meters, so let's go with 8 meters, or we could just say 8 units. For part B, the period of the motion, we know that's always going to be 2 pi divided by n, which in our case is 1 on root 3. So we'd end up with 2 root 3 pi. Alright, so that is having a look at simple harmonic motion problems that involve velocity in terms of displacement.